have you ever wondered how life creates these incredibly complex, perfectly ordered structures in a universe that's always trying to become more chaotic? Well, it happens constantly. Inside of us, tiny machines called proteins spontaneously fold themselves into these amazing shapes, and they seem to be breaking one of the most fundamental laws of physics. Today, we're going to dive into how they pull it off.
So, that's the big question, right? In a universe that is constantly, relentlessly moving towards a state of messiness, how on earth does life manage to build things with such exquisite order? And this isn't some abstract thought experiment. It is happening trillions upon trillions of times every single second inside your own body.
So just look at this. On the left, that's how a protein starts out, as this tangled, floppy, disordered chain. And then, completely on its own, it transforms into that precise, beautiful, functional machine on the right. And the craziest part? This happens in microseconds, every single time, without fail. So how? Why?
And that simple question, why? Well, it throws us headfirst into what really looks like a fundamental paradox of physics.
Okay, so here's the universal law that protein folding seems to be just shattering. It's the second law of thermodynamics. You can think of it as the universe's unstoppable march towards mess. It says that the total amount of disorder, what scientists call entropy, in the universe must always increase, no exceptions.
Let's break that down. The unfolded protein on the left is a state of high entropy. It's a total mess, super disordered. But the single folded protein on the right, that's a state of low entropy. It's incredibly ordered. So the protein is going from messy to neat. How can this drive toward order possibly happen on its own? To solve this mystery, we need to look at the universe's official rulebook, the principle that determines whether any process can happen all by itself. We need to meet the arbiter of spontaneity. And here it is, the Gibbs free energy equation. Now, I know it might look a little intimidating, but it's really just balancing two big forces, heat and disorder. And here's the only rule you need to remember. For any process to be spontaneous, the final answer, that delta G, has to be a negative number. If it's negative, it means the total disorder of the universe went up and the process gets a green light.
Yeah, so just think of Gibbs free energy, or delta G, as the ultimate decider. A negative delta G is basically nature's thumbs up. It's the universe confirming that, hey, even if this one little system got more organized, the total entropy of the entire universe still increased, so the second law is happy. So let's look at the first piece of that puzzle, enthalpy, or delta H. The easiest way to think about this is just heat. As our protein folds up, it forms all these stable new chemical bonds. That process releases heat, which is favorable. And that release of energy gives us a nice negative value for our equation, pushing us one step closer to that spontaneous green light. And then we've got the other major player, entropy, or delta S. This, of course, measures the change in disorder. Now, an increase in disorder is a good thing, thermodynamically speaking. But you see that little minus sign in front of the T delta S in the big equation? That minus sign is about to become a huge problem for us. Because when a protein folds, its own disorder decreases, which means this part of the equation is going to fight us tooth and nail.
And right here, we hit a major plot twist in our story. The protein chain itself is actually a powerful force working against the very process of folding.
I mean, just try to imagine the astronomical number of different shapes and conformations that unfolded floppy chain could take, going from that massive cloud of possibilities down to just one single folded structure. That is a gigantic loss of freedom. It's a huge decrease in the protein's own entropy. This creates a massive thermodynamic penalty that tips the scales heavily against folding. So, if the protein itself is fighting the process, where does the overwhelming force needed to make it fold actually come from? Well, the answer, and this is just beautiful, isn't found inside the protein at all. It's in its environment. It's all about the freedom of water. This whole thing is driven by what's called the hydrophobic effect. See, proteins have these oily, greasy parts that hate being in water. Now, it's not really an attraction that pulls these oily bits together. It's more that the water molecules around them actively push them together, forcing them to hide away in the core of the protein, just to get them out of the way.
And this right here is the whole secret. Look at the image on the left. When the protein is unfolded, the water molecules have to form these rigid, highly ordered cages around those exposed oily parts.
The water is basically trapped in a low-entropy prison. But now, look at the right. When the protein folds and tucks those oily parts inside, all those water molecules are set free. They can tumble, they can spin, they can move randomly. It's a massive, favorable explosion of disorder for the universe.
So here's the absolute key insight. The entropic freedom that all that liberated water gains is so immense, so powerful, that it completely overwhelms the freedom that the protein chain itself lost. That is the secret engine that's driving this entire process forward. So let's go back to our thermodynamic scales. On one side, we've still got that huge penalty from the protein losing all its freedom. But on the other side, we now have two absolute heavyweights, that enormous entropy gain from freeing all the water, plus the favorable heat that gets released from forming all those new bonds. Together, they slam the scales down, making delta G negative and making the whole process of folding spontaneous.
Okay, so we've solved the why of folding, but that still leaves us with another really big puzzle. How does it happen so mind-bogglingly fast? This brings us to the guided pathway. This is what's known as Levinthal's Paradox. The idea is, if a protein had to randomly try out every single possible shape it could form to find the right one, kind of like trying to solve this maze by just taking random turns, it would literally take longer than the current age of the universe. So clearly, folding can't be a random trial-and-error search.
The solution is that the search isn't random at all, it's guided. It's what we call a free energy funnel. So imagine all the unfolded, high-energy shapes are scattered around the wide rim at the top. As the protein starts to fold, it's like a ball rolling downhill. Every correct fold lowers its free energy, channeling it down the funnel, making it move faster and faster towards that single point of lowest energy at the very bottom, the one perfectly folded state.
So we've got these incredibly powerful forces driving the process in this elegantly guided pathway. You'd think the final folded protein would be locked in place like a chunk of granite, but the reality is actually so much more delicate. It exists in what we call a marginally stable state.
Yeah, after all that thermodynamic drama, that cosmic tug-of-war, the final net stability holding a protein together is surprisingly small. We're talking between 5 and 65 kilojoules per mole. To put that in perspective, that's about the same amount of energy as just a few weak hydrogen bonds. The folded state is only just barely more stable than being unfolded.
And this image it perfectly summarizes our entire journey. Protein folding is a thermodynamic tightrope walk. You have the protein's own massive entropy loss, this huge force pulling it towards unfolding. But that is powerfully overcome by the hydrophobic effect and all those stabilizing bonds pulling it towards folding. The result is this marginally stable structure that's reached by a rapid cooperative fall down an energy funnel. And this is really why this all matters. That marginal, delicate stability is absolutely crucial. It's what allows proteins to be flexible, to move, and to do their jobs. But it also makes them incredibly vulnerable. Which leads us to our final and, frankly, pretty profound question. This delicate balance is essential for life. But what happens when that thermodynamic tightrope finally snaps?